next theorem says, for each prime p and each positive integer n, the roots of this polynomial x raised to power pn minus x belonging to zpx in the splitting field over zp are all distinct and form a field f with p to the power n elements. Also, f is the splitting field of p to the power x to the power pn minus x over zp. So what does this say? It says that if you have some polynomial x to the power pn, x to the power p to the power n minus x, and this is some polynomial in zpx. So that means all the coefficients of this field, whatever is the coefficient here and whatever is the coefficient here, they are the elements of this field. And what are the elements of this field? 0 class, 1 class, 2 class up to p minus 1 class. So they are saying for each prime p, whatever are the roots of this polynomial, they would be present in the splitting field of zp. That is all clear. But these roots, they would all be distinct, and the set of all these roots, that would form a field having p to the power n elements. Why p to the power elements? Because here the roots for this particular polynomial, they would be p to the power n. So whatever are the roots of this polynomial, they will form a field, and that field would act as the splitting field of this particular polynomial. Splitting field means you can write this particular polynomial as the product of linear factors. So this is what we mean by splitting field. So let us see its proof. For the proof, we name this polynomial x to the power p to the power n minus x as f of x. So what would be its derivative? Its derivative would be p to the power n would come here in the front, and we would have x to the power p to the power n minus 1. So this whole thing is the power of x, and the derivative of this minus x would be minus 1. So now this quantity won't be equal to 0. Why? Because we have minus 1 here and this thing is not equal to 1. So because the root f of f dash x, because f dash x is not equal to 0, that means f of x would not have multiple roots. So this is according to the theorem that we have studied. Therefore, the polynomial f of x that cannot have multiple roots within it, and all the roots of this polynomial would be distinct. So one part for this theorem is proof that all the roots for this polynomial would be distinct. Now we have to prove that if you consider the set of all these distinct roots, that would form the splitting field of the given polynomial. So for that, what we do, we'll collect all the roots of this polynomial, and we will show that it forms the splitting field of the given polynomial f of x over zp. So we have constructed a new set consisting of all the roots of x to the power pn minus x belonging to zpx. So now to prove this to be the splitting field, first we have to prove this to be the field. For that, what we do, we take any two roots, say alpha and beta are any two roots where beta is not equal to 0. Then if we show that the addition of these two also belongs to this field, and a alpha beta inverse also belongs to this field, then this becomes the field, subfield. Okay. So alpha beta, if they are to any two roots, so that means we are to check whether alpha plus minus beta would also be a root. If this would also be a root, so it will satisfy this polynomial f of x is equal to x raised to power p to the power n minus x. So because alpha is a root, so that means f of alpha is 0. And what was f alpha? F alpha was the same polynomial where now you have replaced x with alpha. So this polynomial is equal to 0. So from here you get alpha raised to power pn is equal to alpha. And similarly, because beta is a root, so from here you get beta raised to power pn minus beta is equal to 0. So from here you have beta raised to power pn is equal to beta. So now we wanted to check whether this is equal to this thing or not. So for that we have just assumed we have just taken the power Pn. Now because we are in Zp, so the power could be splitted into these two terms. And what is this term? This term is nothing but alpha, and what is this term? This term is nothing but beta. So from here we get alpha plus minus beta raised to power Pn is equal to alpha plus minus beta, or in other words you can write alpha plus or minus beta raised to power Pn minus alpha plus minus beta, that is equal to 0. So that means this alpha plus minus beta also satisfied f of x, therefore this becomes the root of f of x. So this is first part. For the second part we will again go for alpha beta inverse raised to power Pn. So it would be alpha power Pn and beta inverse power Pn, or beta power Pn inverse. So this is nothing but alpha, this is nothing but beta. So we have this quantity as equal to alpha beta inverse. So from here also we can say this alpha beta inverse is a root of fx. Thus the set of roots of f of x that forms a subfield of the given splitting field. So next we have to show this form the splitting field. So it is quite obvious that because all these roots, they are distinct in nature, so we can say it is equivalent to the splitting field of f of x, because all the roots are distinct, and the given polynomial could be written as the product of linear factors in f. So therefore the given field is represented by the splitting field of the given polynomial f of x. So I hope this is